Good morning, everyone. First, I would like to thank Is, Jorn, Michael for inviting me here to share with you. Oh.
I was reminded there's one thing. One of our participants is positive tested this morning. Just for your information, be prepared if you like to wear a mask from now on. Maybe it's too late, but just to inform you. So.
Thank you very much, Jorn. As I was saying, well, I'm very happy to be here for the first time, actually, in an ISE school presenting. So today, I'm gonna try to convince you that more engineering topic, probably from what you have been discussing during the week, is also relevant in robotics. So, thank you. So today we are going to be talking about three things that look very different: systems engineering, self-adaptation, and robots with a deep understanding. And I think during the week you have already been discussing a bit about understanding. Yesterday I heard some discussions related to human-robot interaction about it. So I have a very humble goal for today, and it's to inspire you maybe to take a look into this topic. So the first two are topics you can read a lot about. There is plenty of literature about it. There are strong communities working on systems engineering and on self-adaptation. Deep understanding, I still have a big question mark myself. So let's dive into it. Well, Jorn already presented me. I'm an assistant professor at the Delft University of Technology, and I started recently my small lab called CAS, which is quite similar to the Dutch version for cheese, which stands for Knowledge-Based Autonomous Systems. We are focusing on knowledge representation and reasoning, big surprise, but we are also focusing on the software and systems engineering aspects of building an autonomous robot. And we have courses on that with the students in our Master on Cognitive Robotics. And in my group, we focus on the applications for which we get funding. So recently, that's mobile manipulation and underwater robots. They are very different, but the point is our methods aim to be very general, applicable to any kind of engineered system that is autonomous. And robots are one of the most challenging ones, so that's why I find them very interesting. So here are some examples of what we are doing in mobile manipulation and in these topics. So what is the problem that we want to solve? I've chosen three highlights of the last decade, more or less, to motivate a bit autonomous robots, which needs no further motivation, I guess, for all of you. The first one relates more to the engineering aspects of it, and it's ROS. I guess everyone is familiar with the robot operating system. I chose this because it really shapes, in the last decade, what is possible when it comes to integrating an autonomous robot that does a complete mission. So it's not only about detecting that object or planning some motions. It's about detecting the object, planning the motions to it, and picking it, because what you want to have is a robot that is capable of picking any object of a reasonable size, given the size of the robot, for example. And this has made possible that you can get these individual skills that have been developed intensively in the last decades, I would say, achieving great results. ROS is making possible to put them together and try to build a system. And I'm curious how many of you are working on a real robot or on a simulation of a real robot trying to accomplish a task. Raise your hands. Almost all of you. Nice. So this talk is even more for you, basically, because I hope you see some struggles. You can empathize with our struggles, or we empathize with your struggles. The next highlight, this is from us in Delft. We actually did what I was mentioning. We put the state-of-the-art algorithms into a robot that was capable of bean picking in the Amazon Picking Challenge. We won it 1 year, and I have to say there was not much research there. We took the state of the art, we used the best of our expertise to integrate such a system, and it was successful. So it seems like, oh, we can just make autonomous robots now. But you all know that we are far from there, so the third highlight is, okay, when things are really complex and open, we are not yet there. So this is a standard example of a robot falling in the DARPA robotics challenge, right? This is a bit unfair because robots were capable of doing much more than just that in that challenge. But the point is, at some point, almost all the robots got into trouble, big trouble, basically. And under the image of the robot falling, there is the engineering team. And this is a picture not of them designing the system. This is a picture of them probably controlling the system, because some of the robots were only partially autonomous, but the rest of them probably supporting, like, hey, I know about this algorithm, so this is what is happening, right? So there was a lot of knowledge in the room that were part of the bigger system, including humans that were involved in the design of the robot. So this is the picture of where we are, I think, in developing autonomous robots from an engineering perspective. And the question is, so it seems to be a problem to integrate them, right? To make a complete application. So this is the problem of robot control software architectures. Like when we put everything together in a software architecture that needs to run in a real robot. So what is the problem exactly? So I hope you are familiar with the 3-layer paradigm in robotics. Well, every robot has its own architecture, but people typically assign these layers like, oh, we have a deliberative layer, we have an executive layer, and we have some control skills at the bottom. So the top level is doing the planning, so gets the mission, the task that the robot needs to make, the human level understanding of it, basically, and process that into commands that are closer and closer to the variables in the wall, basically, the variables in the sensory motor loops, basically, forces, speeds, pixels in an image, etc. So this, so basically, there is abstraction in the processing in the robot that goes from the mission closer to the environment. And we have this, so it's clear what is in the deliberative layer, the sensory motor control, handles environment uncertainty. But what's going on in the middle part, in that executive? So typically, people use control mechanisms, coordination mechanisms, like finite state machines or behavior trees now are very trendy to coordinate the execution, right? But that's not the only thing that is happening. Because all through the entire architecture, there are a lot of assumptions about the system, about in which conditions the perception is going to work, because our camera is RGB based on flight scanning, and reflection may affect it, for example. So all these assumptions that are spread through the entire system, some of them we actually put them into the executive layer, a lot of assumptions. And those are the ones that are kind of organized, so failures that you expect in your mission, but failures that you expect from components, for example. How many times you were trying to plan a path and move it, or your planning could not find a solution in the middle of the application, right? So that's a problem, how you cope with that. Then you keep trying alternatives, tuning it so that it works in your scenario. Then you put the robot somewhere else and it stops working. It cannot find a plan again, right? So there are a lot of heuristics based on the application and error handling that are going in there. And those are different from the abstraction, the composition that we were talking about. So a concrete example of what is going on here. So our system was basically a pick-and-place system. So I'm not going to explain it. I think everyone here knows how this works. We were using RGDB to detect the objects and their pose. Standard algorithms for more than 6 years ago now, I think. And the architecture looks very complex, but it's actually quite simple in the principles, because it was just gluing together services, not much coordination, because it was not going to be extended, basically. It was a one-time architecture for one concrete task, basically. So the deliberation was very simple, just make some heuristics on which order to pick the objects, and start giving those tasks to our pipeline, which was basically sensing, planning, and acting. Other people use visual servoing, a more closed-loop approach, but this, for us, worked faster, basically, which was the main purpose. You already see some red lines, and those correspond to this middle layer, right? This red part with a lot of if conditions that are completely ad hoc. So this is an example of that. So there are conditions of things that happen to us. The target object was not found. Maybe the pose estimation was not certain enough to be confident to plan the motions, or there was some occluding object, or there was no plan found to move the grip, the end effector, or the object dropped, for example. Many of those that are just cramped in there. And no matter how clean you try to make this, everyone struggles, and in the end there are some conditions here and there in the code that only the programmer knows, basically. In the best case, maybe someone taking care of the design of the system puts it somewhere that is actually more findable. But the whole point is, in the whole reasoning of the robot is not aware of that. There is no reflection on that. There is no declarative knowledge about that in the system. So what happens when all these assumptions that we make when we build our robot don't hold? So I'm not sure if you can interpret this image. I put the robot next to it so that you can figure out which part is the robot. So we are seeing the octomap and also a point cloud and also some grass candidates to pick this object, which seems to be a jar that is on the shelf. And what's happening here is that there is a hole. And actually, the robot has the gripper in that hole. Why? Because for the planning algorithm, it can. So what was happening here is that we were using an RGBD camera, and reflections don't play well there, right? So it thought that there was a hole there. So there were no collisions generated there. The octomap was empty there, so the planner went forward. Of course, this was an early version of the design, basically. So when you are testing your system and the people from planning put their algorithms and the people from perception has just released, like, yeah, this is the collisions that we get. And this happened. One solution was to put the blinders down in the room, and then we get perfect collision, but that doesn't really work in the open world, right? So we got to other solution, which was to use information we have about the environment, because we knew that there were selves in the environment, and we can actually get 3D meshes of that precise self and estimate the position based on what we were seeing, and just add that to the octomap in Moveit. I'm already talking a bit something. I hope everyone is familiar. If not, this is the ROS library for planning that students start with, and everyone later tweaks or creates their own because it doesn't work for the case, right? Which is a bit unfair for what it can do. So we came up with that solution, but there are other solutions possible, actually. Can anyone think of, I don't know if you have run into these issues, what do you do if you don't have perfect collision models out of your perception pipeline? Maybe you don't need them. So if your robot is compliant, we humans sometimes manage through tactile So we may try to go, we detect a collision, and then we avoid it, right? So maybe we don't need a perfect visual pipeline, for example. So what determines which solution do you take? And more importantly, we are making now this solution when designing the system. But if the system is supposed to be autonomous, shouldn't the robot make this decision? More important, how can the robot decide that such a decision is needed? Because here, it's only going to find it when it breaks. And that's actually what happened. We had to 3D print another gripper. Luckily, it was 3D printed. That part are very modular, so we could create a new one a few weeks again before the competition, right? Because we broke that one. So a lot of questions, right? And a lot of options. But it seems clear that we need to move some of the decisions from design to the system at runtime, all right? So this is exactly the approach that we are taking. And the thing is, all these decisions are about the system itself. They depend on the environment, on the mission, but are our decisions about the system? What is in the robot? How does it work? Which components it has? So in our approach is to add one dimension here. So we had basically this dimension moving from the mission into the environment in the abstraction of the processing that the robot is doing. But we need to account for the system also here. So our approach is a bit complex in this table, but I'm going to guide you through it, and this is going to be the organization of the rest of the presentation. So our idea is to separate system concerns because they are not explicitly represented in current robot architectures, basically. So we want to separate that concern. If someone is familiar here with the software engineering, separation of concerns, programming, so that's exactly the idea. Remove all those ad hoc decisions about the system, mix with the coordination of the task. And another important departing hypothesis for us, so our hypothesis is that that's going to work, and using what we already have, it's going to work. This is also something that people consider before, like, hey, if we teleoperate a robot, it can actually do stuff, right? There were, I forgot his name. They did this experiment, I think in 2010 or around more than a decade ago. Everything seemed possible if you have a very dexterous operator of the robot. So the problem is on the decision-making and the control of it that the human teleoperator is doing, right? So kind of and in the last decade, the low-level control, the basic perception, motion planning has advanced a lot. So that means that we should reuse that. And here is a completely different approach. I haven't seen John Laird talk here, but I know the SOAR approach is let's try to build a cognitive system from scratch with these principles. So this is another approach. Let's say an engineering approach to robotics, a bit farther in principle from cognition. Is, okay, we have already all these methods. Let's actually use them. We are not going to reinvent them, basically. We are going to put something on a different dimension next to those to make the system actually work autonomously. So to realize those two principles, two hypotheses, we are going to be using knowledge representation and reasoning methods. I will explain why. And we are going to be using two methods. Model-based systems engineering, that I will talk a bit now, and self-adaptation, which is a topic in software engineering with 2 decades or slightly more of development. And this will result in having systems engineering knowledge in our system, in having architectural reasoning incorporated in that dimension, and to use the current skills, we will have meta models for robot software and we need an adaptation infrastructure. So if we are going to include adaptation, so the system can actually select components, we need how to make that possible. What are the adaptation actions? What are the monitoring, sensing information about the components in the software that we need? So why knowledge representation and reasoning? Apart from that we very much like symbolic reasoning, at least I do, because we need declarative knowledge about this. Why? Because we are talking about metacognition. So if cognition is what the system is doing, coming up with action plans, perceiving, etc., we are going to be talking about how the system is doing that on top of that. So we need metacognition and reflection. And most importantly, we need to be able to reuse our solutions, integrate them in existing systems, and have them extensible. So if there are new skills, we want to be able to incorporate those, right? And all this we can do if we have declarative approach, much more easily. And logic-based. Why? Because engineering knowledge is mostly rule-based, heuristics, and because it's very important that we can verify our solution, basically. We need to be able to trust that the system is adapting. I'm going to speed up a bit. So I'm going to be going through these 4 aspects. The first one is architectural adaptation. So we need to reason how to adapt the robot control architecture. So I'm going to give a crash introduction on one slide to self-adaptive systems. Is anyone here familiar with self-adaptive systems in software? I see some nodding. Okay, so the idea is very simple. So I think a bit more than 20 years ago, there were one of these software crises. So software systems were too complex to manage, basically. And, well, the immediate solution is then we need to automate the managing. So the idea is, well, if we have people managing those systems and we are going to automate that, now we have another subsystem, which is the automatic manager, or the manager of the system. So they formalize the idea in a well-known paradigm in that community, which is the MAPE-K conceptual model, which is basically, we have our system that is now being managed by a managing system. And the managing system, surprise, surprise, follows something similar to sense, plan, act, or so they decided to call it monitor, sensing both the managed system, but also the environment in which that system is executing. Then it analyzes, or perceives, or creates, relates what is seen with its mission, basically. What are the goals, the requirements? And then it also determines which adaptation, then plans how to adapt, how to change the system, and then it needs to execute or act. That's what robots do in the real world. Here is at the meta level, let's say. So very simple. I'm not going to say anything else about self-adaptive systems. There are a lot of methods that work very nicely to balance load on servers, for example. You can find a lot of papers on that. You can also find papers on robotics. But those papers are always simplistic. So the robotic system is simplified to a set of variables that determine the objectives, and they are way more simple than the ones that you get in a real complex robotic applications like the ones that you develop here at TIS, basically. So basically, those methods are very interesting, and actually we use them. But we need something more cognitive, actually, because we need a robotic system manage information that is very heterogeneous, a lot of knowledge that is heterogeneous. You cannot apply one simple Markov network, basically. A robotic system has many other aspects, right? And the problem is that we want to manage all that together in one system. Okay, so after all this, I'm going to show you a video. I want you to pay close attention to it.
All engine running. Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11.
I hope you are paying attention. I was aiming for a higher volume, sorry, to wake everyone up. But I think a rocket going up the sky, it's always something to wake up. So while everyone, I think there was a spoiler everywhere, right? This is the Apollo 11 mission. So why I'm showing this video? What made the moon landing possible, or not, according to some people? So some may say the rocket technology, right? And von Braun. Software? I actually, well, yeah, a bit, but you will be surprised. Yeah, actually. More? Engineering? In general, yes. So there was a lot of engineering, many disciplines, from rocket science to software. So I'm going to talk about another one, which is systems engineering. So this is a paradigmatic example of an engineering program that required to manage complexity. And that's what systems engineering is about, basically. So let's talk about that knowledge that make that possible, and why I think we need this also in robotics. So systems engineering is basically a framework to integrate diverse engineering disciplines or specialties. And here, especially at the East Fall School, you can see how robotics is also very interdisciplinary. So aerospace is also, even if there is a word for it, there is people there working on many different things, from chemistry to material science to flight dynamics. And the systems are very complex, right? You don't do systems engineering and complex architectures for a very, very simple system. So according, for example, to IEEE, and that's why I put this definition, systems engineering is the interdisciplinary tasks which are required through a system's lifecycle to transform customer needs, requirements, and constraints into a system solution. And I want to stress here customer needs. So this is kind of a business-oriented definition, but if we talk about robots that interact with people, so it's our needs, basically. They are systems that we build for a reason to render some value to us, basically. And this is very important. This is very important because in the end, we want the robot to do maybe not to put that object there, basically. We want the robot to order the shelf, for example, in the supermarket. And sure, they are related, but sometimes it's not exactly the same thing. And there are other values involved. So maybe I want the robot to put that there, but not if my hand is there, because there's another requirement that maybe it shall not crush my hand with the jar it's trying to put, right? So this satisfaction of the customer needs, this thinking of the high-level values of the user is what distinguishes systems engineering as a discipline that integrates all the engineering disciplines to achieve a common set of requirements and mission of the system. So in this case, for example, the customer need could be considered to replace that person with a robot, actually. That's what they needed. In a concrete case of a certain logistic infrastructure in their warehouse, basically. Maybe not in another one. So we are talking about the relation in between the mission and the system. This is where systems engineering comes into play, because there is a lot of knowledge generated in that discipline on that relation, and we need that relation in our systems. So I'm going to speed up a bit. So systems engineering has more than 50 years of or well, almost a century, depending on what you consider it starting. But only recently, it actually started being automated and create formal models. So before, everything is in thousands of documents, basically. That's the main artifact of work for engineering teams. Lately, with model-based systems engineering and taking inspiration from software, how many of you have heard of UML? Okay, so now there is SysML, and second version is happening as we speak, basically, multiple releases now. It's a language to describe the activities and the results of the activities of engineering a system and the decisions being made and the architecture of the system. So this allows automation. And this is the key here. So we can leverage that for the knowledge in our robots, right? If we have formal knowledge about that. So the view, there are many approaches to systems engineering with different vocabularies. Some are shared. There are associations about it. So we are developing our own approach with a complex name, ISE and PPOA. It's also partially based on software. The important aspect is that it's based on the functional architecture. The focus is on the architecture of the system and the functional one. And what's the difference in between the functional architecture and the physical architecture? So the functional architecture describes what the system has to do and how you can decompose those into sub-functions, whereas the physical architecture is how that is finally implemented in components that may be hardware, physical, but we also name physical to those that are software, because they are real things. There's some programs that live in the computer, whereas the functional architecture is an abstraction. We abstract a representation of what should be happening in the system. So we have been already applying that to model robotic systems to understand their properties, for example, and how our architectural decisions affect their properties. For example, in this case, we had a sensing skin developed by TU Munich, Gordon Chen's group. We worked together in an European project, and we had different options to use this skin to avoid collisions. One option is the simple one, that was stopping when the skin was detecting a collision. We actually work on a more advanced version in which the system would be actually avoiding the obstacle. But that was working way slower. So for what was needed for the application, it's a trade-off. Also, it was not safe enough because the reaction was not fast enough to avoid collisions. So we could not close the online planning loop fast enough, for example. So these are decisions based on properties of the system that you need to take on which components, which algorithms to use. And the idea is maybe the system should be able to choose and apply one or the other one dynamically, right? So I'm going to go faster. Later you can check in my slides and read more about how we model this functional architecture, which goes from the decomposition from the mission into different aspects. So pick and place application. Then we need, for example, to be able to move the robot safely. That means to be able to sense obstacles, but that also means to be able to obtain collision-free trajectories. This is already a decision at this level. So instead of using visual servoing, we were obtaining collision-free trajectories, and then we were planning and executing them, basically. But still, we haven't decided with what are we going to be doing that. This is a definition of something to do. Obtain collision-free trajectories. You may apply multiple algorithms for that. Okay? So that's the key idea here. We are separating the what to do from the how we are going to do it. And this reflects the dependencies in between functions. To be able to do one, you may need some other ones. But actually, they are connected because the product of one function may be the input for another one. And those are reflected in the interfaces that are also important. But it's also important the behavior, how the flow of execution goes from one function to the other. I'm not going to go in details of that, but I'm just going to mention that for the moment, we are being able to model this and to use this knowledge, the one about which function depends on which one, to make decisions on what is available and what not. Another aspect, apart from the functional architecture that I want to mention, is another properties of the system that are not that easily declaratively decomposed, which are the quality attributes. We are talking about things like safety that are inherent to an entire system. A robot may be safe or not if it collides with people at a certain speed, for example. So that's the result of multiple algorithms, but there is one property for the system. And it's up to the engineers to try to come up with metrics for that attribute, for example, safety. There are multiple ways of measuring safety, and it will depend on your application, for example. So you have a mobile robot, probably you want to keep a certain distance to obstacles or avoid impacts at speeds higher than something. So which criteria to use depends on the application. And they are typically not that declarative models. You may actually create declarative models for that, but it's difficult sometimes. So that's still a challenge, but it's an important aspect. And how everything comes together, this is a very complex diagram, but the important thing is when you design the system, you start decomposing the functions. And then you check how your solution matches the quality criteria for safety, etc. And then you choose algorithms and components that match that criteria, following certain heuristics. So in that way, you go from the mission, that is the big function of the system. It's to pick and place objects, for example, or to navigate underwater following a pipeline. That's another example we are working on right now. That's the general mission, and then you decompose into functions, and then you start allocating the functions to your algorithm. This algorithm is going to be responsible of doing this or doing this other thing. And for that decision, you check, you make trade-offs using the quality attributes and other criteria to select, right? So you move from the functional architecture into physical, completely allocated parts in your system. Are we going to be using ICP for post-estimation? I think someone was working on post-estimation. So there are many possibilities to do that, right? So this is about systems engineering and why it can fill in knowledge that relates the mission of the robot with what the robot is, that bunch of algorithms that we are putting together. Another image. Does anyone? Well, it says there, right? So this is the mission operation control room. Actually, there are multiple control rooms. You have seen that in the movies, I'm sure, a lot. This is probably not one of the biggest one. I think the launch room is way bigger. And this is the end of the mission. That's why people are not looking at the screens anymore. But if you imagine, and you have probably seen the stress films in which they are with the countdown and everyone is checking everything. Does that remind you of something we have seen before? In this presentation, actually? Were you paying attention? See some nodding. Yeah, right, it's like when you're in a robotic competition and everyone is, what's happening? Why it's not finding the object? What's going on? Do we have a result from the planning? No. So it's very similar, right? So that's basically what inspired me many years ago, actually. Also, when I was with my robot, reading the ROS logs, 2009, 2010, all times in ROS, and saying, maybe this should be automated. Maybe what I'm doing, it should be the robot doing, right? So I'm going to just guide you through what we have done with all this inspiration and ideas, how we have implemented them by leveraging the existing skills, which is in the big community ROS based. So I will just quickly guide you through them. So our approach, we call meta control, because if the robot is, if we are creating the control of the robot in general, concretely what we are focusing on creating on this meta control on top of it, right? So the self-adaptive model, in our case, the system that is managing is, we call it meta control. It follows more or less the monitor, analyze, plan, execute structure, or the sense, plan, act, whatever you want to call it. But we use a runtime model of the architecture of the system. That's the knowledge that we use to adapt the robot control software. Concretely, this is the meta model. Does everyone knows what a meta model is? If not, if you know what an ontology is, then you are good also. There are papers on meta models versus ontologies, so I'm not going to enter into that. But basically, this is how we represent the architecture of the system. You should already be familiar with the functional hierarchy. That's one part of the functional architecture, the simpler part that connects functions with each other. So we know which one depends on which one, right? So we are capable of modeling that. We model that with functions, and function designs are versions of the physical architecture. So options to perform a function, to solve a function. So if this part is design information, well, the system is actually implementing at runtime that design. And that's different from the design itself, right? So this is difference between an object and a class, right? Something, a running artifact. So we need to capture the state at runtime. So is that function actually working or not? Which safety associated to it? Which concrete value? Not the one we want. The one is actually rendering, right? So we have also elements to capture the runtime state. Okay? And with these elements in our meta model that we call Thomas's teleological ontological model for autonomous systems, teleological because it's about the goals of the system, ontological because it's about what the system is. So it should be able to model situations like a component failure or a functional failure of an entire subsystem, of the quality attributes, what's the value of the safety, how is that impacting the system. So our hierarchy can model that. One example, very simple, model manipulation problem. The Yumi is building a pyramid with both arms. In this other video, it's starting to do it with one, then our colleague touches one, safety alert, so that arm is blocked just in case, but the system is capable of continuing with using only one arm. So it's a different strategy that requires different components. Now the system actually has to move the base to have reachability, for example. So how we model this with our meta model, so as to be able to reason about these options. So we have a function which is to pick and place blocks, and we can do it with one arm or with two arms. With two arms, what you've seen is a completely scripted state machine in the ABB software, actually. So we cannot reflect internally on what's going on, but we can reflect on there is an alternative. And this alternative is actually a bit more modular because we were using some ROS components to be able to navigate to the pose. So to navigate, we were not using standard move base, but actually the robot uses markers to locate and to calibrate its position with the table, basically. So basically, to move relative to the table, it needed to calibrate the position. To calibrate the position, we actually had different options depending on the lighting conditions. And the system can reason on all of these things as far as there is knowledge on that. Our meta model allows you to define the depth of that knowledge. It's depending on what you actually need. If some parts of the system are actually a black box that you cannot adapt, then you don't need to represent them. Following up, this meta model has been implemented in a logic-based representation, so formalized in all, formalized in all, and using Swill rules to account for quantifying things, quality attributes, for example. So we have rules that determine, very, very simple rules that determine that a function can only provide its functionality if all the components that are required are present and not in a failure status, for example. So there are very simple rules, but composed allows you to really diagnose what is going on in the system. And not only the running system, but the different options. Because another option may also not be available if it depends on the same component, for example. So it's very simple, but it's very powerful to at least reason in a way that is general and reusable in many, many systems. A completely different example. I promised you some underwater robots. And you got a talk by Peter, right, the other day. So I hope you are familiar with thrust and all these things. So in this case, there were 8 thrusters in this ball-like robot. This was a different European project. So the adaptation problem was first to allocate power to the thrust to achieve the motions required in the system and the right controller overall for those thrusters. There were a couple of options, a PID controller and a fuzzy controller that had different requirements on how much power was available on the thrusters. So this looks very much the same as the previous model, but it's actually written in SysML. It's very similar to UML. The system, the different controllers, what they require, a certain performance of propulsion, which is the abstraction of what the thrusters are doing, so that we can reason independently of the technology of the thrusters. This is just for the marine robotics fans. You not only activate or deactivate thrusters, you need to change the metrics that allocate thrust to each one to achieve the desired propulsion overall. So our reasoning uses the rules to, from the state of the thrusters, understand which functions are in danger because we don't have enough thrust in a certain thruster available, etc. And conversely, we decide the reconfiguration of thrusters based on that. And all this corresponds to the monitor and analyze when diagnosing and the planning and executing the adaptation when deciding which thruster to activate and which allocation matrix to use. Not everything is symbolic here. We actually did some machine learning because quality attributes are harder to model that with symbolic reasoning. So how do you decide to change to a different configuration for your navigation system in a mobile robot, for example, based on safety? You have many possibilities to configure, for example, move base. I'm not sure if any of you have played around with move base for a mobile robot, similar to Move It. You need to decide a lot of parameters, and it will work or not for your application. So the question is how to decide, for example, the best configuration for the dynamic window approach algorithm that is being used there. So we tested multiple, and together with a master student, and Darko, one of the postdocs working with me, we thought, well, maybe we can create a model that maps which environment we are in, what are the properties of the environment, and what safety is to be expected of each different configuration, basically. So we trained machine learning model, so it was capable of keeping or predicting at runtime. So you have two graphs because there is one that is the configuration being applied at the moment, and the one in green, and the other one that was rendering actually a better safety. So the system, when the safety threshold was broken, would switch to the one with a better safety. I just wanted to mention that we can actually validate, and we are starting to work in Remaro on using different logic languages to basically explore the adaptations that the system would do. So we want to verify that our adaptation engine, our meta control, will stay in a space that is the one compliant with the mission. I'm going to skip the rest. I'm going to go for this is another example in a different robot. So the big question is, does meta control solve our problems? So if we go back to a robot that is having a partially empty point cloud that should not be empty at a certain spot when picking something, how do we model this with which we have seen till now? Because here is basically the environment affecting. There is no problem in any component of the robot that is running till something actually breaks and maybe detects the safety of the controller of the manipulator triggers, basically, because of the torque applied. Actually, it did not, because this is an industrial robot, really tough, and the shelf is really light, so that was the problem. So it cannot cope with this scenario, because there is more knowledge required. We need to integrate this with the knowledge in the other dimension that we were discussing, the one that you are normally working on, the one about the mission, about the objects in the environment. We want to map that information, understand that information in terms of what the robot is doing, in terms of picking. The goal is picking that object and not breaking anything. That's also a very important requirement. We need to understand what the robot is seeing based on that. And here I use understand. That's the deep understanding in the approach that we are taking. The robot is able to relate the sensory input with its algorithms, with the assumptions that are being made, but also with the goal. The goal is not to break anything while picking that. Imagine that the robot is reaching for someone to rescue someone, and there was something on the way. So maybe some debris or something. Doesn't matter to break or the debris if the goal is to reach something. Even maybe damaging the robot arm. That's not the problem, right? But how can a robot make that decision? Only if it has deep understanding of the relation between what it's seeing, what it can do, what it is, and what it's reaching for. What is the overall goal? Because I ran out of time, that's basically the main message. That goes into many, many other things, but I think, so what time exactly it is?
6 minutes to answer a question.
Okay, then I think I will stop there, basically. So, just wrapping up, I think systems engineering is also for robots, not only for engineers, and it's for robots to do at runtime, and that's the real challenge. How to represent all that knowledge, and how, mostly because there is a lot of heuristics on that, right? Engineering heuristics. Why we choose certain algorithms are not others. Well, we can do hypothesis testing. How can we generate also those heuristics? How can we have the robot test hypothesis and come up with that? I think there is a lot to investigate. I got inspired by space engineering, but I also had a slide about other projects on archaeology that I didn't have time this time. I think hopefully in the future I will present results because those are actually too early results. So I'm happy to stop here and take questions.
Thanks a lot for the presentation. So in the fall school, we have a lot heard about cognitive architectures. You have talked about software architectures. Can you say a little bit what is, from your perspective, the relation between both?
That's, thank you very much for, for the question. So software architecture is what we actually put in the robot. The software that we put. We can organize it according to certain principles, and I think that's what a cognitive architecture is, that abstract idea that the end code is representing, right? So, to my understanding, a cognitive architecture should be able to exploit, exert declarative knowledge, basically. And here in the proposal is we should actually, to have reflection, the system really should know itself, have knowledge about itself. And my proposal is that the right level of abstraction to include or not to miss, I'm not saying others are not needed, but knowledge about the system is efficient, is useful to use, even if it's not at all similar to what humans do. Because we have no clue how we are adding up in our head, right? So here I'm proposing something completely opposite. Like if the robot is planning this way, the robot should know about how it's planning explicitly. But because we have that knowledge available, we don't have the knowledge available yet of how we do that in our head. And that's, I think, why we actually cannot use it yet for meta-reflection. So it's a different dimension, but actually I call our architecture also cognitive because it's based on declarative models. That's the core idea. And in that sense, I think there is a lot of common ground.
Watch your head.
Yeah, thanks for the talk. I have a question regarding the quality attributes. So one would be, what are the quality attributes that you have considered in your work? And I would be second interested in how kind of general these are. because you said they are like kind of application specific and depending on the application. So the question arises, if we kind of model that, is there kind of an overarching theory or like some abstractions that we could use to kind of more flexibly insert kind of these quality metrics in new applications, so to say?
Yeah, so I think I probably was not precise or correct enough. So there are general definitions of quality attributes, and this is the kind of things engineers do, right? They come up with certain standards. So there is something called safety. And then how you measure safety, that's really application dependent, right? But we all agree that there is something safety, and we assign certain behaviors, certain effects, we label them with safety. This is safety related, right? And there are more or less precise definitions of why is safety and not security, etc. So security is another one, safety. We have considered safety, energy, and one that is not directly considered as a quality attribute, but more related to the function, which is performance. Like you define a performance for how well am I moving, for example, how fast, differently, for example. Those are the ones that we have considered so far.
Okay. Any further question?
Coffee.
Do you want some coffee? Okay, thank you very much.
Thank you very much.